All right, ladies and gentlemen, what we're going to get into now is kind of a follow-up from our last little video segment, which we were talking about what matter was, and we focused in on volume, mass, and weight in that video lesson. Okay, so a quick review of that. Make sure that we're comfortable with the definitions. Make sure you're comfortable with how you measure them, what units they have, and what they're dependent on. So are they dependent on temperature? Are they dependent on location? Neither, that kind of stuff as we work forward with this, okay? And what tools we use to measure those things, all right? Once we know these basic ideas of what mass, volume, and weight are, the next piece of our puzzle is to start to classify the actual matter into some different categories, okay? So we're looking at different categories for matter, all right? Now, the notes here are really good, but I like to break this idea down even further for us. So if we take a look, we have, first of all, we have matter. And matter in itself can be broken down into two different categories. Okay? And the first of those two categories is called the pure substance. Okay. Now, pure substances they are chemically pure. What we mean by that is that these substances have their own properties. They have their own boiling points, their own melting points, their own densities, their own reactivity, their own pHs, their own toxicity, that kind of stuff. Okay. Their own radioactivity, possibly. So they have very distinct, measurable chemical properties that we're looking at for a pure substance. Okay. Now, if you have a pure substance, that pure substance can be broken down into even more categories, okay? So a pure substance, we can say, falls under the category of either an element or a compound. We'll tackle element first. Elements, okay, they are the building blocks of nature. Okay, we have 118 elements. They're on the periodic table. They actually are easiest to identify because if they're not on the periodic table, they're not an element. Okay, whereas we have lots more compounds and molecules and mixtures and other things, but elements are very, very specific. They have to be something off that periodic table. Now, within the element itself, typically we think of elements as breaking down into individual atoms. Okay, so if you have a single particle of carbon, a single atom of carbon, that's its smallest building block you can have, okay? Anything smaller, if we break down that one atom of carbon, remember carbon has 6 protons, it has 6 electrons as long as it's neutral, and it has anywhere from 6 to 8 neutrons depending on which isotope of carbon we're talking about. But carbon itself can break down into its smallest piece of being an atom. Same thing for every element, okay? Now, anything smaller than that, and now you're dealing with subatomic particles, which no longer retain those individual chemical properties, okay? So really, a single atom of carbon is about as simple as you can get to maintain those properties, okay? Or an atom of aluminum, or an atom of nickel, or an atom of iron, whatever element you're talking about, all right? So atoms are things like carbon, nickel, iron, helium, those kind of things. Now, if we keep moving along here and start talking about compounds, compounds are when we chemically combine 2 or more atoms together, and they should be different atoms, okay? So I have oxygen and I have hydrogen, and I chemically combine those 2 together. That's a compound, all right? So compounds, when we take a look at them, they also can be identified by formulas, okay? So H2O for water, or maybe you have sodium chloride for salt, okay? Notice how we have 2 different elements inside that compound, but they are chemically bonded together through what's called a chemical bond. We'll talk about that a little bit more in a little bit. And that creates new properties, okay? That is why we can call a compound a pure substance. You might be thinking, wait a minute, you're combining more than one thing. How can that be a pure thing if you're combining it, all right? Because it actually takes on its own new set of properties, chemical and physical properties to that substance, okay? Let me give you an example of that might help clarify a little bit. All right, so we know hydrogen. Hydrogen in our world is highly explosive. Hydrogen in our world, if you light a match to it, it's going to explode, and it's not real safe for us to keep around, okay? Oxygen. Oxygen in our world supports combustion, okay? So if you have pure oxygen around, you actually have a fire hazard with pure oxygen. Any of those oxygen tanks are actually labeled with, explosion warnings, that kind of stuff, because more oxygen you have is supporting things burning or combusting. Okay, so hydrogen explode, oxygen supports combustion. Water puts out fires. Okay, so once you take hydrogen and put it with oxygen and chemically combine the two together in a ratio of 2 to 1, which we make water molecules, H2O, now we have a substance that actively stops combustion from happening. Okay, completely opposite type of properties to it. Okay, hydrogen, oxygen are gases at room temperature. Water is a liquid at room temperature. Okay, very different chemical and physical properties because we've chemically bonded them together. Give you another example, sodium chloride. Sodium chloride is table salt. Okay, sodium, if you know anything about sodium metal, the actual metal of just pure sodium, non-ionized, it's actually a really silver soft metal. We'll talk more about it later. It's actually explosive in water. So if you take sodium and put it in water, it will explode. Okay, we're actually going to do that in class. It's going to be fun. Chlorine gas by itself is toxic to people. Okay, so chlorine gas, if you breathe it in, it's a precursor to mustard gas, World War II type of, World War I, World War II, one of those two worlds, and it will kill you. Okay, so you have sodium, blows up in water, chlorine, toxic, kills people. Put them together, you get salt, delicious on French fries. A nutrient our body needs. Now, we'll argue that a lot of people get too much salt, but it is an essential nutrient we need. That is how different they become when they are chemically bonded together. Okay, so you have this idea that you truly are creating a whole new thing. You might be thinking, I've heard this term molecule before. Where does molecules fit into this system then? Because we have elements and compounds. A molecule is not an element, is it? Is it just another compound? Is something fancy about it? What is it? Okay, so really, molecule is kind of a unique term that is used in a little bit of both sides of the stuff. Okay. So on our little graph here, an element can actually be a molecule also. Okay. Now, when you get a molecule of an element, you get things like N2, which is nitrogen bonded to itself. Or you might get H2, which is hydrogen bonded to itself. Well, we don't want to, in terms of our stuff there, okay? So molecules come from the chemical combination of two things put together. So N2, H2, those are molecules, all right? Molecules also can come from two separate things. So this is also a molecule, okay? So water is also a molecule because you have a chemical combination of two things put together, okay? You might be thinking, oh, so anytime you chemically bond, you have a molecule. If the chemical bonds are two different things, it's also a compound. So all molecules are compounds, and that wouldn't be true because some molecules are elements, okay? But you could say all compounds are molecules. Is that true? Well, let's take a look at it and let's think about it, okay? So this would make sense, right? As long as we have a chemical combination of two things, we get a molecule. All right, so then things like diatomic nitrogen works, things like hydrogen works, things like water works, and then we get to sodium chloride and say, oh, is that a molecule also? That's where we get to run into a problem because when sodium and chlorine bonds together, they do create chemical bonds, but they don't make distinct packages, okay? They bond a different way. They bond through something called an ionic bond, all right? So as a result, we don't get a molecule of salt, okay? So we wouldn't use the term molecule for things that don't form individualized packages, okay? And it's going to come down to this difference in bonding, where things that covalently bond or molecular bond, where they share electrons, they make packages, which then we can call molecules. Things that ionically bond, they don't make packages. They make more of a lattice structure of repeating patterns, we don't call them molecules, okay? Which makes molecules a little bit harder to understand. Things I want you to get from this though. One is that if you have an element, you can have an atom of that element, or you can have a molecule of that element if you have more than one there, okay? You can also think that some of our compounds, if they make sharing of electrons, can also be called a molecule, okay? We will get into more detail on this idea of what molecules are later on, but that's kind of the level at which we want to be at right now in terms of the separation between those two things. Now, that being said, if we look over here, this would be an atomic view of atoms. This would be an atomic view of molecules. This is also an atomic view of molecules. They're all in their individual packages. This would be a single element. This would be an element. This would be a compound, okay? So you can have a molecule here that's of an element. You can have atoms of an element. You can have molecules of a compound also, all right? We don't have an example up here of a compound that does not form molecules in these images right here, all right?